Today is a quick recap about LightGBM. It's basically a radiant boosting tree with two extra features. The first one is radiant-based one-side sampling. It will exclude a significant proportion of data instances with small radians and only use the rest to estimate the information gained. A conventional implementation of the radiant boosting decision tree need to scan all the data instances to estimate information gain of all possible split points. Therefore, the computational complexity will be proportional to both the number of features and the number of instances. Then this makes this implementation very time-consuming when handling big data. And data instances with different gradients play different roles in the computation of information gain. In particular, according to the definition of information gain, though instances with larger gradients will contribute more to the information gain. Therefore, when downsampling the data instances in order to retain accuracy of the information gain estimation, we should better keep those instances with large gradient. And that is the purpose of gradient-based one-side sampling. It will keep all the instances with large gradients and perform random sampling on the instances with small gradients in order to compensate for influence to the data distribution. When computing information gain, the feature like the mechanic introduce a constant multiplier for the data instances with small gradient. Specifically, gradient-based one-side sampling first sorts the data instances according to the absolute value of their gradients, and to select a top A multiplied by 100% instances, and this it randomly sample B multiplied by 100% instances for the rest of the data. After that, it will amplify the sample data with small gradients by a constant 1 minus AB when calculating the information gain. And by doing that, we put more focus on the under-trained instances with large gradients and without changing the original distribution by much. The second important feature of LightGBM is the exclusive feature bundling. In a sparse feature space, many features are mutually exclusive, which means they never take non-zero values simultaneously, and we can safely bundle exclusive features into a single feature. And by carefully designing the feature scanning algorithm, we can build the feature histograms from the feature bundles as those from individual features. And in this way, the complexity of histogram building change, and we have to consider two important things. The first is which features should be bundled together. And to decide that, first we construct a graph with weighted edge, and the weight will correspond to the total conflict between features. And second, we sort the features by their degrees in the graph in the descending order. And finally, we check its features in the order list and either assign it to an existing bundle with a small conflict, or we create a new bundle. And the second thing is how to construct the bundle. We construct a feature bundle by letting exclusive features reside in different bins. This can be done by adding an offset to the original feature value of the features. For example, suppose we have two features in the feature bundle. Feature A takes value from 0 to 10, and feature B takes value to 0 to 20. And then we add the offset of 10 to the value of feature B, so that the refined features take value from 10 to 30, and after that, it is safe to merge feature A and B and use the feature bundle with range 0 to 30 to replace the original features of A and B.